So your question is, you are confused how to start the project and where to start the project. So let's go here. I have given you some description with respect to your project. So let's open up the description first. Okay. So this is the description I gave. You are not sure how to or where to start the project. Okay. First is the design specification. So what is this specification? So what have I asked you? I asked you to design a connecting rod. Okay. So to design a connecting rod, first you have to come up with some kind of specifications. For example, what is the length? Typical length of a connecting rod. You can pick up any engine, any IC engine. Maybe if you have an IC engine for a car, okay, they will have particular dimensions. So you have to first get some of the dimensions associated with a car engine, for example. That will give you an idea about what is the typical length of the connecting rod, what will be the typical width of the connecting rod, what kind of materials are used for the connecting rod. Okay, so here we can see size specification. So first you start with some kind of design specification. What is a design specification? You want when you want to manufacture any product, you should specify what is the size of the product, what kind of loads act on the product. For example, on the connecting rod, you will have compressive loads, right? So if you look at it, it is going to be compressive load. It is a variable load. Sometimes it is compressive load and maybe sometimes it is zero load. So depending upon where the connecting rod is located on the crankshaft rotation angle, this is the crankshaft, you will have zero load or some kind of compressive load. So you have to specify that load. Okay, once you know what kind of loads act on the connecting rod, then you will be able to do some calculations for stresses. Okay, so that is why we need some kind of load specification. Then material specification. Why do we need material specification? We have already gone through static failure theory, for example. So to use any of the static failure theory, we need material property like yield strength of the material. So we need material specifications. What kind of material are we using here? Okay, there are many materials according to standards, maybe AISI standards, ASTM standards, and we have the unified system standards in the second chapter, according to which several materials are identified. Once you identify the material properties also can be identified. For that material, you will get the material properties. Okay, how are you going to manufacture it? By machining, by stamping, by combination of methods, right? So what kind of manufacturing processes are required? And manufacturing processes also influence the material properties in some way. Sometimes if you do some kind of heat treatment process, that will influence the material properties. So if there is any influence, you will also have to see that. How will the connecting rod fail? Think about some of the failure modes. We have already seen in static failure what kind of failure we have. Okay, so the connecting rod is made out of a ductile material, then the failure is going to be ductile failure. It could be fracture, it could be yielding, it could be something else. For example, buckling. So these are some of the failure modes. So you have to get some data regarding how the material can fail. You have to again go online and research how the things are failing. For example, maybe I showed you, or let's see, if you come online on campus, especially within the university campus, you should be able to get some papers from this particular website. Okay, so for example, I'm looking connecting rod, and let's see failure modes. If I search, I might get some papers associated with it. See here, analysis of failure modes and design improvement of eccentrically loaded connecting rod. If you are especially on campus, maybe you have access to some of these papers. Don't try it outside. If you are outside the university, maybe you will not have access to these papers. But if you are inside the university, you can access these papers from university internet. Okay, and you can see here, for example, this is connecting rod for some application, whatever the application is. You can see buckling type failure, right? You can read through this paper. Okay, so that will help you. Different failure modes are here. I can look at more papers. Specifically, if I want automotive applications, I can write automotive, another search term here, and search for it. So it will give me for automotive application, mechanical and properties, and so this is regarding some kind of manufacturing processes. Again, failure modeling for titanium alloy in special purpose connecting rods. You can see there is also design and analysis of connecting rod using ANSYS software. You can directly go to this paper, cite this paper according to this paper. This is the information given, and try to go through that. Okay, so this is how you get information regarding work. Go to sciencedirect.com. Again, can you guys see the website? This is a very important tool. If you go through my second lecture, I have given some of these links. Okay, so sciencedirect.com is one website. There is also another website which is jstore.org. If you go this is a British website. Specifically, all the research connected with many of the British Royal Societies, they are published here. So again, let's check connecting rod, failure modes, and click on it. Specifically, we can see simulations. I want to see simulations directly. Okay, so type in simulations, and you might get some information. Specifically, we are not getting anything with respect to connecting rod here. Okay, so in that case, let me put a quote mark within it, so that will force the system to search. So we don't have any paper associated in this particular website. So we don't have anything related to connecting rods. Okay, so but in general, Science Direct could be a very good resource for you. Okay, is it clear?
Yes, doctor. Doctor,
Okay.
specification I can get them from the standards, right?
The specifications you can get it from brochures. Go Google search. You will see typical connecting rod sizes for automotive applications. And 1 second, I think I typed it wrong here. Specifications. You can just Google search, and you will see many applications for different kinds. For example, diesel engines here. You may in fact get some brochures from existing industries. You can go through this. We can search for brochures. Maybe some of the companies will list what kind of specifications they have. You have to look around in Google and look for the specs. Okay, and with respect to the standards for the materials, etc., the brochures will list some of the standards associated with the material. Okay, let's taking some time to open your PDF files. 1 second. Okay, so this is a catalog. You can see this is a brochure, some company's catalog, and it may have some information regarding connecting rods. So maybe you need to look around what kind of data we have. Okay, bent or twisted connecting rod. Go through these brochures like in this way. You have to search around. It may not be easy to get the data you require, but you have to search for it. Okay, so use online internet resources, use research papers, which is the sciencedirect.com, and you will get much information regarding your connecting rods. Don't copy everything from the papers given here. Don't copy it word for word. Understand what they have done and do similar work. Okay, you can do similar work, but you will have to do your own analysis using ANSYS software. Okay, so let's go back to that Word file. So this is regarding the design specification. You can come across failure modes, cost, etc. Then you will have to think and come up with what are the constraints in the with respect to design. What are constraints? These two, design specifications and design constraints in your project, are extremely important. If you do not have these two, you cannot proceed with the design. Okay, even in your senior project, this is the same case. Design without design specification, design constraints, you cannot do much. Okay, now geometric constraints. Again, you have to come for a particular automobile. There may be a limit to the size of the connecting rod. For the length of the connecting rod has to be below a certain size, for example. So that is a constraint according to design specs of other parts. Your IC engines and a crankshaft, they are separated by a certain distance according to design requirements, and based upon those design requirements, your connecting rod size will be limited. It has to be less than or equal to some size. So that you have to get. What about the shape? The shape also may be constrained. Depending upon your design requirements, shape of the cross section, the shape along the length of the connecting rod. If you look at the connecting rod, it has a particular shape here along the length. So diameter is smaller here, it is bigger here. I mean, there are some constraints because you have to attach this to the crankshaft, this end, and this end to the engine piston. Okay, so you have to specify all those constraints. There may be manufacturing constraints. Okay, and operation and maintenance constraints. All these you have to specify. Whatever you can understand and specify, these two parts are important. Once this is done, you have to do some kind of kinematic or kinetic analysis. How does the connecting rod move around? What kind of acceleration and velocity changes it has while the connecting rod moves around? Okay, why this is important, especially with the dynamic analysis. These could be very important to know what are the forces which are acting. Okay, and in order to figure out even static analysis at certain positions, by doing this kinematic and kinetic analysis, you will realize at certain positions the conducting rod has maximum forces acting on them. At that particular state, you can do some kind of static analysis. Okay, To do static analysis, you have to know in which position forces are maximum, where the forces are maximum, etc. So you will have to do static analysis. How do we do static analysis? We have the static failure theories and we will apply those theories. We have learned about static failure theory today. So up till this point, you should be able to do for now. The dynamic analysis, I'm going to teach this particular chapter, especially fatigue analysis in the next chapter, and then you can apply that. You will do all hand calculations. That means you will apply the formulas, what we have seen in the slides, directly apply it and calculate what are the stresses, identify where the stresses are maximum, possibly maximum in the connecting rod, and identify those locations and calculate the stresses. Okay, so this part is very important. Again, you will do hand calculations for fatigue analysis once I go through that chapter, and any fracture analysis if it is possible, if you know there is a fracture inside. But mostly we do not assume any fracture and continue the calculations. After you do the hand calculations, then using your FEA software ANSYS, create a model, do static analysis. You can also do dynamic analysis and check. If possible, you can also do topology optimization. Okay, so what is topology optimization? I will present a small slides, few number of slides, and explain to you what is topology optimization, and then you will try to apply that in finite element analysis. ANSYS has an automatic way to apply this, and I will show you that as well. Okay, and finally, also material selection, material index. You have to come up with some kind of material index for the connecting rod and choose based upon Ashby's charts provided in your book. You will try to come up with some kind of materials for connecting rod. Okay, and finally, the detailed design will have drawings and conclude it. Okay, so shape optimization or topology optimization is some kind of a bonus mark, and buckling analysis. If you do buckling, because anything under compression undergoes buckling. We have already seen one example here. One of the papers we just saw the failure. I think I opened one of the previous papers. Yes, here you can see this is buckling failure. Under compression, it undergoes buckling failure. So if you are able to do this, apply simple formulas and do that. And if you can do that for connecting rod, then you will get similar, you will get bonus marks. Okay, and especially if you do buckling analysis and finite element, you will get much more marks. Okay, so do you have some idea now?
Yes, Doctor, that was really helpful.
Okay. Okay, so anyway, this is recorded, and those who are not online, I would advise, let your other group mates also, they can do the project well. Okay. So let's go back to the slides and continue with the course. Okay. Again, let's recall what we went through. I'm going to rewrite exactly what are the concepts we went through in static failure theory. Okay. So let me write static failure theory. Okay. Can one of you tell me what are the failure theories we have gone through for ductile materials? Because if you don't recall these concepts, it is no use if I continue like this. Okay. Ductile materials. What are the failure theory we went through? One of you?
Maximum shear stress.
Maximum shear stress theory. Very good. So what does maximum shear stress theory say? Tau max, which is equal to sigma 1 minus sigma 3 over 2, should be less than or equal to SSY, shear yield strength. What is SSY? In the case of most of the materials with equal properties in tension and compression, it is yield strength and tension from the tensile test over 2. Okay, so this is the maximum shear stress theory. Sigma 1 and sigma 3, these are the maximum principal stresses and the minimum principal stress. Maximum principal stress and minimum principal stress in 3D. Okay. 2. Any other theory we went through? Again, maximum shear stress theory, and then there is a distortion energy theory. This is the most important theory, and all your finite element software, they print out what is called as von Mises stress, and this stress comes out from distortion energy theory. So the von Mises stress is defined as sigma prime. Since in 3D we have for the stress components, we have 6 independent components. We cannot compare all the 6 components to yield stress value and then decide. It will be very difficult to do that. So what does the distortion energy theory provide? It will help you to find a single number, single stress value, or what is called as the equivalent stress or von Mises stress, von Mises, or equivalent stress value, a single number which you can compare it to the yield strength and then say whether failure will take place or not. Okay. So according to distortion energy theory, this von Mises stress must be less than or equal to SY. Okay. And of course, we can add in the maximum shear stress theory and von Mises theory, factor of safety n to the yield strength values. Okay, so how did we define von Mises stress? As square root. Inside the square root, we have divided by 2, and we successively take the difference between the principal stresses and add them up. That's all. So this gives us the von Mises stress. Then for ductile materials, any other theory we have one more theory. If the tensile properties are not equal to, let's say this is SYT, we have to use SYC. If the tensile and the compressive properties are not equal, in that case we use Coulomb-Moore theory. Okay. And in Coulomb-Moore theory, since we have different properties, here it's very similar to the maximum shear stress theory, except we have slightly different equation. What is the equation we have? In the numerator, we have the principal stresses, and in the denominator, we have the properties. Sigma 1, the highest value, okay, and SY tensile property here, minus sigma 3 compressive property. Sigma 3 can be positive or negative principal stress value, but in the denominator we have the compressive property should be equal to 1 over n with the factor of safety. So this is the condition we have. If we are within this envelope, then no failure. So in terms of equation, if I find the factor of safety n value, if this n value is greater than 1, then no failure. If n value is less than 1, and that means definitely failure has taken place. Okay. So this is with respect to the ductile materials. In the case of brittle material, we have only one theory, Coulomb-Moore theory, which we have seen. Now, besides these failure theories, there are also other failure theories in your book. Okay, and you can go through that as well. So in the Coulomb-Moore theory, we have the same kind of formula, sigma 1 over ultimate property in tension minus sigma 3 over ultimate property in compression must be equal to 1 over n. And depending upon the n value, whether it is less than 1, if it is less than 1, failure, greater than, less than or equal to 1, it is failure, greater than 1, no failure for the brittle material. Now, in case of brittle materials, we also had failure if fractures are present. So this is another theory, linear elastic fracture mechanics, and this is what we were going through. Okay, this is where we are, and let's continue with that. Okay. Last class, we went through an example problem where we have a centrally transverse crack, transverse with respect to the load applied, and we evaluated what is the at what stress the catastrophic failure will take place. We also evaluated what is the value of n, factor of safety associated with the fracture. Okay, now we'll go to another example problem, a similar problem. We have here a plate with has a width of 1.4 meters and the length 2.8 meters. So let's draw the plate again. The plate is a 3D plate. Okay. Oh, so this is the plate we have. Oh. It is 1.4 meters width. So clearly we are given this is 1.4. The height is 2.8. Okay. Okay, then what do we have? In the direction of 2.8 meters, we have a 4 mega Newton load. It is a load. What is given here? It is a load. Okay, not a stress value, but the load. Load is 4 mega newtons. It's 4 into 10 power 6 newtons. It's a huge load. Okay, then inspection procedures, they detect, not will detect, it detects, procedures detect only through thickness edge crack larger than 2.7 millimeters. So maybe there's a crack on the left edge or the right edge. Maybe we assume it is in the crack is on the left edge. So in that case, I have to provide some gap here to identify the crack. So let's see. Stop halfway here because there is a crack. And I'm going to identify the crack with a V here. Okay. So we cannot see the crack, but with a dotted line, I have put the crack. Edge crack is there, 2.7 mm. So I have exaggerated the length of the crack. This crack length is 2.7 millimeters. Very, very small crack compared to the length here, which is in meters. There are two titanium alloys given in table 5.1. Let's go back to this table. This is the table, and maybe this is 6V. Okay, two different materials, titanium alloys, and each alloy has a certain KIC value. We can clearly see the 4V alloy has higher KIC value and can absorb more energy before crack propagation than the 6V alloy. Okay. However, we can see the yield strengths are different. Here, KIC value is greater, but yield strength is lower. Okay. Let's continue here. Are being considered for this application, for which the safety factor must be 1.3, N value must be 1.3, minimum weight is important. So I have to choose between the two alloy, one alloy. So which alloy should be used? I have to identify that. What are the conditions? The condition is minimum weight. My plate must be minimum weight. Okay. So here, what are the constraints? We have the length and the width fixed. I cannot change anything, but notice that we are not given what is the thickness of the plate. The thickness of the plate is missing, and we assume T. Okay, T is the thickness. How do I solve it? Okay. What is the condition? The condition is minimum weight. Okay. So let's write the equation for mass. Mass is rho times volume, which I can write rho times area times length. And for the plate, we have whatever the material is, rho value for titanium alloy, whatever the alloy is going to remain constant. It is not going to change much. And the area of cross section in our problem is going to be width 1.4 times thickness T. T times length. We already know what is the length. Length is also fixed, 2.8 meters. So all the values are fixed except T. So if I want minimum mass, my T value must be minimum. So T should be minimum in our solution to minimize the weight or the mass. So we are clear here that we have to choose the minimum T value depending upon the alloy, titanium alloy we choose. Okay, so let's continue now with the other calculations. The safety factor is 1.3. So I'm going to write N is equal to 1.3. Whatever data we are given, we apply a load 4 mega newtons. So we can calculate stress. Force or P is equal to 4 into 10 power 6 newtons. Calculate stress. Stress becomes force over internal force over area. Internal force is going to be the same external force P, because whenever I take a section anywhere on the plate, the internal force will be equal to P. Okay, and we know what is the area of cross section, 1.4 T. 4 into 10 power 6 over 1.4 T. Let's open up MATLAB for all calculations. Okay. Now let us try to express sigma in megapascals so that it will be easier. This 10 power 6 will always give us in megapascals. So we can neglect this 10 power 6, 4 over 1.4, that is the value we want. .8579 over T. megapascals. So this is the stress. Okay. Nominal stress we have calculated. Let's go back to the problem now. Here, what we are asked, we have to choose the material. Okay, we must come up with a criteria that will help us here. Since there is a crack of 2.7 millimeters, which means our EA here is 2.7 into 10 power minus 3 meters. We have to use this value. So first, since the crack is present, the quantity I will calculate is Ki value. Ki is the stress intensity factor, and the formula what we have seen before is beta sigma root pi EA, and it should be in megapascal root meter value. What is the beta value? To get the beta value for an edge crack, we need to go back to one of the graphs we have seen earlier. And remember, it is an edge crack with a tensile load. So this is the appropriate graph here. We can see from the graph what are the B value and the H values. So B value, what is B here? We have seen from the problem already. This is the value 1.4 given in the problem. We already denoted here 1.4. Okay, and then the H value is also going to be equally 1.4 because 2 times H is 2.8 and 2.8 over 2 is equal to 1.4 meters. That's the H value. Now, what are the other values? A size, we already know 2.8, 2.7 into 10 power minus 3 meters. Get the ratio A over B. A is 2.7 times 10 power minus 3. B is pretty large value, 1.4. We can assume it is very near 0. Whatever the value it is definitely the ratio A over B is going to be extremely small. Okay, very, very small value. You can check. What's the ratio? 2.7 over. You can see 1.4 times 1000 will become 1400. You get 0.0019. Very, very, very small value, near 0. Right. Go back to the graph. It is near 0, and clearly, whatever the H over B may be, it all converges to a value near 1. Let's assume. So this is 2, this is 1. So the value here will be 1.5, and half of the value will be 1.25, less than half of that. So 1.125, maybe 1.12. We can assume beta equal to 1.12. That's what I'm going to assume. Approximately 1.12. Assuming this beta value, we can evaluate what is Ki, the stress intensity factor. Okay, substitute 1.12 times sigma value. What is the sigma value? Stress we have already calculated, 2.8571 over T in megapascals, consistent units, pi times 2.7 times 10 power minus 3. Let's get an expression or calculate the value for this guy. a value here because I want to use that, and I 1.12 multiplied by S1 multiplied by square root 2.7 pi over 1000. 0.2947 over T. So this is the stress intensity factor in the unit megapascal root meter. Now this value, if no failure is to take place, okay, no failure is to take place for the given problem. This is the problem. Then this value Ki value should be less than or equal to the KIC values for the two materials. Okay, so what is the KIC value for the two materials? Go back to the table. We'll find the value. For, I'm going to just write titanium 4B. The value of KIC is 115. And 6V it is in megapascal root meter. These are the KIC values. Now let me write the expression for T. So if I rewrite the expression for T, T should be greater than or equal to 0.2947 over KIC. So this is the expression I get. Now if I put the larger value here, obviously if I use this material, my thickness will be lesser value than using the smaller value here. Okay, so definitely I'm going to choose the material which has larger KIC value, and if I do that, over 115, I will get the least T value. So least T value greater than or equal to 115 I get I use long to be more accurate, and let me multiply by 1000 to get it in millimeters rather than meters. So I get more accurate value 2.5627, so I can approximate to 2.57 millimeters. Okay, so this is the thickness, minimum thickness, least thickness, which I can select for the material, which is Ti4V. So, now I also need to check for this particular thickness value, what is the stress? Because the original problem, let's see if we are given any other yield strength value. Okay, so from here, I see the yield strength is 910. I need to check for this material 910 megapascals for the titanium alloy, very high, nearly gigapascal. Whether my stress is below this, otherwise yielding will occur. So I also need to check with the particular T value. Okay. So let's calculate the stress. Stress, we have already seen the formula. Formula is 2.8571 over T. Okay. And we have to substitute T in meters here, or no? Yes. Yes, in meters. Okay. So we need to be careful. T in meters. Okay, so let's calculate. Go back to the MATLAB, and it's the 2.857. This one is S1 value. Okay, so we can use that. So the stress, actual stress, is S1 divided by the T value in meters. So I used T here divided by T exact value, or maybe I just use 2.57 because that is what I use, and multiply by 1000, that becomes in meters, and the result should be in megapascal. And what do we see here? We have pretty high value of stress. The sigma value for this thickness is 1111.7 megapascals. So let's check using the usual formula as well. Instead of using the formula here, 4 times 10 power 6, that is the force 4 meganewtons by 1.4 times thickness T. 1.4 is in meters, so 2.57 is the thickness, and we have to divide this by 1000 to convert it into meters. We have done that. We want the result in megapascals, so we can divide by 10 power 6. So I can get rid of this 10 power 6, and yes, same result. Okay. So we have 1111.7 megapascals, which is greater than the SY value for the material. Okay, so let's see again. If you look at the SY value for the material is 910. Okay, so we have to reduce the size of the thickness. Okay, so how do we reduce? So this is not the solution. We cannot use 2.57, maybe some other value slightly higher than 2.57, and let's try to figure out the value from the yield strength value. Okay, so in that case, now again we do another calculation. 2.8571 over T is in meters, remember, and this should be less than or equal to SY equal to 910 megapascals. So in this case, what is the result? T should be greater than or equal to, remember the result on the left hand side is in megapascals already, and T will be in meters. If you calculate that, 2.8571 over 910. Let's convert that into millimeters, that means 10 power 3. What is the result we get? Let's calculate that. S1 is 2.8571 multiply by 1000 and divide by 910. We get the value of thickness 3.14. millimeters. So maybe we need to go for a thickness 3.14 millimeters, t greater than or equal to 3.14 millimeters. So this should be the thickness here. But if we calculate what is the thickness based upon the value 55 here for the thickness, we can also try it just in case we want to be sure that thickness value is not less than 3.14. So KIC for this is for 6V titanium 6V alloy. KI, if we calculate according to the formula, KI is 0.2947 over T. Must be greater than or equal to, less than or equal to, not greater. Less than or equal to KIC value, which is equal to, go back to the slide, for 6V it is 55. Okay. And T value, which means must be greater than or equal to, in this case, 0.2947 over 55 and into 10 power 3, so that we get it in millimeters. The thickness to the MATLAB, we need to see where 2947 is KI, so that is stored in KI. We use KI times 10 power 3 divided by 55. Because we are going to, okay, we have to use capital KI, so 5.36 millimeters. Now this value is pretty higher than this value, so the best option is to go with this thickness. Okay, so this is the best option for the least weight material, to avoid any failure due to crack propagation and failure due to yielding. Okay, because we get yielding here, if we assume T is 2.57, we definitely get yielding, and that is also a failure. So we have to select the material. So final answer will be the selection of material and thickness value. So the material is titanium 4V alloy, should be used with thickness T is equal to 3 point, at the least, so greater than or equal to 3.14 millimeters. So this is the answer. Okay. So for your problem, the thickness must be minimum 3.14 millimeters with 4V alloy. Is the solution clear?
Yes, doctor.
The solution is clear? Okay, so if you have any doubt, ask me now. So we need to check a couple of properties. One is crack propagation, next is yielding. If both doesn't take place, then the plate is okay. Otherwise, the plate is not okay. Okay, so let's see here. Here, they have assumed a higher, okay, we completely forgot the factor of safety. I'm sorry, I think I forgot about the factor of safety, which was given in the problem, 1.3. We completely forgot about that. So, which means in all the places here, we have to include the factor of safety 1.3. Hold on a second. Stress, we calculate the stress intensity factor, which is fine. 1.12, the stress intensity factor is okay. The only point is this KIC value, we have to include a factor of safety and should have included over n here. Okay, so 1.3. So that's the mistake we did. 1.3. Okay, so if we have the factor 1.3, then your T is it 1.3 or 1.4? You have a factor of safety 1.3. So we need to multiply 1.3 here. Okay, multiply by 1.3. 0.2947. Okay. New. So that will change our calculations and it will be simpler in our case. Ki times 1.3 over 115 times 1000 to get it in millimeters. So we have with this 3.331. 3.331. So here the result must be 3.33. No, so just 3.34. We can assume 3.34. That should have been the thickness with the particular thickness value 3.34. You can see 3.14 here. Okay, 1 second. Let's calculate with 2.8571. What is this value for the sigma 1? So S1 value. Go back to the MATLAB. S1, we have to 2.8571 is the stress, if I remember, yes, over 3, which is 3.34. In meters, 1000 multiplied. The stress value, we get 855. Okay, so now we are within the limits actually. Not actually within the limits, we need to check 855.43. Okay. 855.43. But we also need to check with Sy over n value, because there is a factor of safety and we need to check if this is less than this value. Okay, so what is the stress value we have? Yield stress value 910 over 1.3. 1.3 with the factor of safety we get 700, so which is equal to 700 here with the factor of safety, and therefore the value 855.43 is greater than 700 megapascals. So yielding will take place by failure will take place by yielding. So we need to calculate according to this 1.3, and 1.3 is 700 here. Okay, so with this value, if you again calculate T, we have 2.8571 over 910 times 1.3. factor. Okay, S1 over 910 times 1.3 times 1000, so 1307. That will give us directly in millimeters, 4.08. So let's take it as 4.1 millimeters. So with the factor of safety, we get the thickness must be at least 4.1 millimeters. This is the least option we have seen. Okay, with again we have to calculate here with the factor of safety. Here I see over n 1.3. Here we multiply 1.3 and the result will be 5.36 times 1.3, which will be a higher value. We get 6.97, so yeah, 6.97. So among the two options, what we see, 4.1 millimeter is the least option, and this is the, with the factor of safety, we have to choose a material 4V with 4.1 millimeter thickness, and that will not give us any failure. Okay. So don't miss the factor of safety. If you are given that value, you should not miss the factor of safety as well in the calculations. Now the calculations here, you can see 4.1 millimeters. This is the one we have to choose, just as we have done, and the other calculation gives this. So between the two values, 4.1 millimeter is the right choice. Let's try some problem for Coulomb-Moore failure theory. Now what do we have here? We have a wrench. Okay. Should we take a 10-minute break now?
Yes, doctor, no problem.
Yes.
Okay, so let's take a 10-minute break and we will meet again at 9:20. Okay, 9:20 we will meet. Okay, so let's continue now. Okay, can you guys see my screen?
Yes, Doctor.
Are you?
Yes, sir.
Okay, very good. Okay, so let's continue with another problem here. Here we have a wrench, just like one of the previous problems we have solved. It is made out of cast iron, machine to dimension. The force F required to fracture this part can be regarded as the strength of the component part. If the material is ASTM grade 30 cast iron, mostly I think maybe a brittle material, find the force F with Coulomb-Moore failure model and modified Moore failure model. Okay, so let's see here. We need the properties of this particular steel. Let's see from the solution if we can get the properties of the steel. Okay, 1 second. Okay, so we have here table A24 gives you the ultimate tensile strengths, KPSI in tension, tensile strength and compressive strength. So these are the values, and let us see. 30 cast iron is a brittle material. Okay, so it is classified as a brittle material. So that is why we are given the ultimate strength of the material in tension and compression rather than the yield strength. And the concentration factors here are set to unity. Just to simplify the problem, they are set to unity. Okay, previously we used some kind of concentration factors. Here, in the case of ductile materials, we used concentration factors. Here we are going to assume it is unity. But let's see if we have the concentration factors already used from one of the previous problems. Let's see here. It's definitely not this lecture. Should be 16th. No. Okay. Section 1. We don't have it here. Maybe 15. I think this is the problem we solved. Just want to check what is the concentration factor we may have used over there. Okay, so here we have KT is 1.6, KTS is 1.4. I'm going to use the same concentration factor over here. What is the problem here? Example 5.5. Example 5.5. Okay. KT 1.4 and the KTS value 1.6. So let's use these values. For brittle materials, we will definitely require the stress concentration factors right at this section over here, where the stresses are going to be the maximum. Okay, so just like the previous case, we write the force vector and locations as usual. Okay, or the location of the force F in vector form. We have the X, Y, and Z. In exam, if you are not given the X, Y, and Z, you have to assume where the origin is and what are the X, Y, Z coordinates. You have to appropriately assume and then write it. Okay. So here we assume the origin is 0 here at this point O. Now the X value will be, according to this calculation, 2 plus 12 plus 2, 16. X value at this point is 16. The Y value is 0 and the Z value is positive 15. Okay. Then we need the point here. Again, RA. You can directly write. Yes, X value is 2 plus 12 plus, no, it's just 2 here, right? So we are looking at location A, 2. The Y and Z values are obviously 0. Okay. What is F? It's the force vector. And here find the force F. So F is unknown. 0 minus F is 0. We want to calculate the moment at A. Remember, we also have a shear force. But first, if we have a torque acting on the shaft here, stepped shaft here, then we can neglect the transverse shear force effects. Okay, and then do the calculation. So first let's calculate moment with respect to A due to the force F. Is going to be RF minus RA cross product F. And then we write I, J, K values. What is the second row? The second row is going to be RF minus RA. Subtract these two, 16 minus 2, 14. 0 in the J component, and we have 15. All right, and the force is 0 minus F. 0. To expand this, right, plus, and minus here, and we will expand according to the row here and the column over here with the F value. F becomes positive, negative of negative becomes positive. Yeah, I have a class. And let's write the quantities here. So we have 15I minus 14K minus 14K. Okay, so this is the moment acting at A. These are the moments acting at A due to the force F. Okay, so with respect to I, we have 15F. Okay, which is with respect to the x-axis, we have a torque. So we can write it in the array format as well. 15F, 0 minus 14F. These are the moments. So we have a torque with respect to x-axis, and we also have a bending moment with respect to the z-axis in the negative direction. Remember that F cannot be negative, F has to be positive. So this is a negative quantity. And the bending moment is with respect to negative z-axis. Using right hand rule, you can see the bending moment is with respect to z-axis is in this direction, and you can take any point A on the top. If you consider that that is subject to a tensile stress sigma xx. Okay. The compressive stress will be equal and opposite in the point on the bottom. What will be the shear stress component? Since we are looking at this particular surface here, the shear stress component is most probably going to be in the direction of z due to the torque. The torque is with respect to the positive x-axis. So this is the way torque acts, and it acts in the z direction here. So the shear stress component is xz. So we have to draw the stress element here on the xz plane over here like this, the stress element. Okay, so once we draw that, we can see in the xz plane what is the direction of the stress, and then we can figure out what are the components. So let's first draw the stress element here on xz plane. When I look from the top view, I'm going to see my x-axis here, stress element over here, and the z-axis going down like that here. X is here, z going down. My shear stress on the plane x here is going down this way. So that fixes the shear stress direction, and there is also sigma xx value here. So this is tau xy, xz, the sigma xx. Sigma zz is 0. All right, so we have all the stress components ready. Now, since x and z axis are located in this way, it is a little bit problematic to draw our Mohr circle. So what I'm going to do is draw the same stress element in a slightly different way by rotating this guy by 90 degrees in the anti-clockwise direction. So that will help us draw the Mohr circle in a more sensible manner according to our sign conventions. So let's redraw our stress element. Rotating by 90 degrees, this is what I'm going to get, x and z. Again, draw the stress element, but this time be careful in denoting the directions of your shear stresses correctly. So on the plane perpendicular to the x-axis, the shear stress is in clockwise direction here. So now, with respect to the z-axis, it is in the anti-clockwise direction. Now it is right. Clearly, this is a positive shear stress value. See, we have the sigma xx value here. Okay. Now that we have with the correct orientation the stress element, we can further go down and calculate what is sigma xx. According to our formula, kt times m over I times c. Kt value is 1.4 according to our calculations in the previous problem. The bending moment value with respect to, since we are calculating with respect to z-axis, the bending moment value is 14F. But remember, we are calculating at the point A, which is tensile. So I will take the positive value here, 14 times F. Okay, over I. Since we have taken the stress concentration factor, that means for the smaller diameter of the shaft, I have to calculate what is the moment of inertia is going to be 1 inch. Since it is 1 inch diameter, I have pi over 64 times 1 raised to the power 4. 1 is just 1 inch, so we need not worry about that. And here we have the C value will be half of the diameter, which is the radius. Radius will be 1 over 2. 1 over 2. So that gives us, in terms of F, at the point A, what is the stress value? So let's clear everything, just in case we have some in memory some variable declared. I'm calculating xx, stress in the xx direction will be 1.4 times 14f. 14, we cannot calculate f, so leave it as such, and divide by pi over 32. So we can cancel this guy, divide it as 30, divided by pi times 32. So multiply by 32, divide by pi. That gives us SEX value. So here we need to be a little bit careful about the units. This is an inch, inch power 4, and this is inches, and we get the result here, inch cube in the denominator. However, for your moment, we have taken all distances in inches, so it will be pound inch, and pound inch per inch cube will give pound per inch square. But we want in kpsi. The units are right, yes. We want the result in kpsi. So we have to divide by 1000, and we are going to get 0.1996 in kpsi. 96 F, remember, F also has to be in pound force, kp psi, kilopounds per square inch. Let's similarly use the torque value to evaluate the shear stress. We will neglect any transverse shear stress because we have the torque here, and torque dominates. So we have kts T over J times the radius C. KTS is 1.6, and the torque value we have calculated above. With respect to x-axis is 15F. Okay. Then we have the J value, which is pi over 32 times 1 power 4 times 1 over 2. Cancel 32 and becomes 60. Again, we will calculate in kpsi by dividing by 2. Okay. Back to the MATLAB. We have the SXX value, replace with 16 here, and this becomes tau x z value, and we need to replace 1.4 by 1.6. 0.6 times 15 by 15, and then multiply by 16, then divided by pi and 1000. No. So this gives us the tau x z value at the point A is 0.1222 F kp plus 1. Okay. So we have the normal stress and the shear stress. Let's go back to the problem here. And we need to figure out to use the Coulomb-Moore theory or modified Moore's theory. We actually did not go through the modified Moore theory. So I think I will skip the modified Moore's theory as such, and we will just stick with Coulomb-Moore's failure model. Okay, so let's see here. In the Coulomb-Moore failure model, we need the sigma 1 and sigma 3 values. Okay, so we have the material property already here. We can use that. So how do I calculate sigma 1 and 3? Use the Moore's circle method. However, to use the Moore's circle method, we need the F value. We do not have the F value. So we can eliminate F and draw the Moore's circle, or we can use the formula. So let us say we are using the formula to figure out what are the sigma values. So in that case, we will write the formula sigma xx plus yy over 2 plus or minus square root sigma xx minus yy over 2 the whole square plus tau. Since we are working on zz, so instead of yy we have to write it as zz, sorry, because these are the two components we are working on. So be careful about representing it correctly. And tau xz square. So this is the formula we are going to use. I do not know what are sigma, whether it is sigma 1, 2 or 3 values. We have to remember that one of the principal stress values is also 0. Why is it that case? If you write the stress tensor in 3D, you will realize that one of the values is 0. We have sigma xx value 0.1996 F. 1996 F is one of the stress values. 0.1222 F is xz value. Okay, so this is the xz value. The rest of the values are obviously 0. So from here we can realize that one of the principal stresses is 0. We do not know whether this guy is sigma 1, 2 or 3 because we do not know whether the other two sigma principal stress values are positive or negative. We need to calculate here and figure it out. So let's write the equation here. Sigma is equal to sigma xx value 0.1996 F and zz is 0, so divide by 2. We have plus or minus square root. Again we have 0.1996 EF divided by 2, z is 0 again, and then plus we have 0.1222 F the whole square. Okay, so we can simplify this. Okay, so if I divide by 2, I'm going to get 0.0996 9.8 F plus or minus, and here we have something. Calculate the value in the square root. I have here 0.1996 F, whereas 0.1996 right here as XX. Yeah, divided by 4 over here, and then we have tau xz square value, get 0.1578 F. So F, the value F is always positive. So this means we have a positive sigma 1 value and a negative sigma 3 value, while sigma 2 is 0. So we have 1 and 3 calculated here. I'm going to write S1 is the sigma 1 value, and I'm going to take SXX over 2 plus tau max is going to give me 0.2576 F. Okay. F, that is the value. This is in kpsi. So let's write it explicitly. This is kpsi. While F is in pounds, I have to substitute in pounds. F in pound force. Okay. The sigma 2 value is 0, and sigma 3 value we need to calculate. Minus tau max at minus 0.058. F kpsi. This is also kpsi. Okay. So we have the sigma 1 and 3 value. Since one is positive and another guy is negative, we use the Coulomb-Moore theory in this form. Sigma 1 over SUT minus sigma 3 over SUC. Just about 2 minutes, it will be done.
No, because I want to know how to work this classroom.
Oh, classroom.
Use this one, I already work and this already thing.
There is a software actually.
And I already downloaded the software, everything.
2 minutes I will come.
Okay. This one, that's 108.
Yeah, 0?
108.
108. Okay, doctor. Okay. Yeah. Sorry for that. So here this should be equal to 1 over n with the factor of safety for this problem. Let's see here if we have any factor of safety being used. We do not use any factor of safety. Let's say if we assume a factor of safety equal to 2. If you assume, let's see here, no. Yes, let's assume a factor of safety 2 and then calculate what is the F value. Substitute for sigma 1. Sigma 1 is 0.2576 F. F is common, so I'm going to take it commonly outside, divided by SUT value. Under tension, ultimate tensile strength is 31. So write it as 31 kpsi. Since we have all the units in kpsi, that is fine. The compression here we have sigma 3 is negative 0.058 F. Since F we have taken commonly out, you can forget about the factor F here. And then in the denominator we have 109 equal to 1 over 2. We can solve for this. Okay, very easy to solve. Go to the MATLAB. We have S1 and S3. Okay, so on the right hand side 1 over 2 divided by bracket open. We have this entire term. So we have S1 over 31 plus. Why plus? Because we have a negative sign here, negative sign here. Both become positive. Is 3 divided by 109. 109. So that should give us in pound force what is the value. And the value of F is, okay, so strictly for our condition should be less than or equal to the factor of safety, 1 over n value in this form for avoiding any failure. So your F should be less than or equal to 64.27 pound force. Anything above this force will cause failure for your system. Let's check the answers. Without the factor of safety and without the stress concentration factors, you get 176. Remember, we have used stress concentration factor KT and KTS in addition to a factor of safety 2, and therefore we get a value here. This is the value, sorry. We get a value much lesser than that. Okay, so is the solution clear? Is the solution clear for you guys?
Yes, yes.
Okay, so we are done for today. Next class, I think I will stop on the example problems. We are done with this chapter. In fact, there are more example problems given here. You need to solve it by yourself using the same method. Try to solve the other example problems in the chapter. We are done with this chapter, and next class we will go for the new chapter on fatigue. By the way, guys, do you want to have a quiz next week? Is it possible to have a quiz? Not next week. I said it is a take-home quiz, right? Since we have it on the first 4 chapters, do you want me to revise next week? Do you guys want to have a revision of the 4 chapters for the exam?
Yes,
I cannot hear you.
Yes, no problem, Doctor.
Okay, so we'll do a revision of problems, and we will also go through the material index problems again. Okay, so next week, today is Monday, no, Tuesday, sorry. So on Thursday, we will do a revision of the topics. Okay, so see you guys, and I will meet you on Thursday.